It's time now to look at a very interesting class of regression models. These are called generalized linear models, and a very important case that we use a lot in science is logistic regression. And this also has a hierarchical version called a generalized linear mixed model. But today I will only introduce the generalized linear model with the special case of the logistic regression example. So let's start with an example as usual, right? So imagine doing an experiment like the following. What we want to do is we show our participants different words, one after another, in a sequence. So for example, dog, hat, what's that third word? Run and hug, right? And so then they see a blank screen, and then they are prompted to respond to what was the third word that you saw in that list. So they have to give a response now that could be either correct or incorrect, right? So they have to type in that response. That's what that box is there for, right? So that's what the experiment is about. And so what we're going to do is we're going to increase the set size, the number of words that people have to see on the screen. And we want to know whether their accuracy of recall is going to be affected by the number of words that they're going to see. You can imagine what's going to happen, right? As you increase the number of words, accuracy is going to tank, right? They're going to go down, right? Okay, so let's take a look at this data. This is also in our bcogSci package, right? This DF recall data set. So if you look at this data set, it's important to note that I have repeated measurements from each subject here, okay? So again, I'm ignoring that detail. I'm going to treat these data as independent and identically distributed. I'm going to fix that problem at the end of this set of lectures. But for now, I'm ignoring the independence assumption here. And my responses, the dependent variable now is no longer millisecond reading times or pupil size or anything like that. These are 0-1 responses. What distribution corresponds to a 0-1 response? It's the Bernoulli, right? We studied that at the beginning. So here we have the 0-1 response. So an obvious thing to use here would be the Bernoulli likelihood, right? And the generalization of that is, of course, the binomial, right? So that's why you might sometimes see in software either Bernoulli or binomial. So don't be confused by that. It just refers to the number of trials, right? Okay, so we have some other information in this data frame that tells us which session it was, which block and so on, and what the set size was. This is the interesting thing for us, right? So there are different numbers of words that we are exposing our participants to, right? And so again, as before, what we're going to do is we're going to center our set size. This is a vector that contains numbers like 2, 4, 6, and 8. We're going to center it so that it's either negative or positive, but with a mean of 0. Right? That's what centering is doing for us. And the reason we are doing this is that we want the intercept to have the interpretation that it represents the grand mean. Okay? The grand mean of what? I will just explain that in a minute. But in this model, it will again represent the grand mean. Okay? That's an interesting and useful thing to do statistically. Okay, so let's look at what we have in this data set. So just to quickly confirm that we indeed have set sizes 2, 4, 6, and 8, right? So we're going to look at the accuracy change as set sizes increases. Theoretically, what I expect, from common sense, right, is that my accuracy will go down as the set size increases, okay? All right, so notice also that I have multiple measurements for each set size. I've got 23 measurements here for each of these set sizes, right? So I have repeated measurements on this, right? So a simple model that we can start with, which is technically not exactly right for this situation, but it's almost right, is the generalized linear model with a so-called link function. Okay, so the way this works is as follows. We're going to model the 0-1 responses, the correct, incorrect responses, or rather the incorrect, correct responses, as a Bernoulli distribution. Remember that the Bernoulli distribution has only one trial, and there's some probability of success represented by this theta parameter, right? So we are getting these 1s and 0s from subjects coming from some Bernoulli distribution, and this index n that I've put under theta represents the row ID. So every 0 and 1 in the data frame, let's go back. Every 0 and 1 in the data frame is being described by some Bernoulli distribution, and there is some theta associated with that row that is generating that data. This is a generative process that I'm describing, when I write down this model here. Okay, so this model looks pretty straightforward, but what we're going to do is we're going to put a little twist to this situation. The twist is that we're going to take those theta sub n's for each of those rows and take the odds with those thetas and then take the log of that. So this is called, this term inside the brackets is called the odds, right? So if the probability of success is 50%, for example, the odds are 1 to 1, right? That's how we speak. So often in day-to-day life, people will say, what are the odds of it raining today? What they actually mean is, what is the probability of it raining today? In statistics, odds has a different meaning than probability, okay? So it takes the probability value theta and converts it into a ratio in this way, right? The ratio of probability of success divided by the probability of failure, okay? So we're going to work on this log odds scale. And we're going to fit a linear model on this scale. Well, the reason is that we want to stay with the linear modeling framework because it's so convenient. It has such generalizability. If I have multiple predictors, I can plug them in and can do a lot of things now, right? But with this Bernoulli generative process, I'm kind of limited by the nature of the 0, 1 outputs, right? They're discrete outcomes, right? So I want to convert it to some kind of continuous outcome, and this is the transformation that I will do to achieve that, to achieve a continuous outcome. So my dependent variable will now become the log odds, okay? And I'm going to fit a model that's going to, let me just write it out. What's going to happen is that I'm going to have log, I'm just going to drop the subscripts just for convenience now, and I'm going to say that I'm going to fit a model not on 0, 1 responses, but I'm going to fit the model on the log odds scale, right? So I will have some predictor. The story remains exactly the same. That's the beauty of the generalized linear model, that we stay with the regression modeling framework. We don't have to depart from this general framework that is so well established, but now we've got our predictor, so call it, I don't know, set size in this case, or let's say it was centered set size, right? We have centered set size, and so basically this is the standard predictor as before, right? This is some vector of values, and we have an intercept and slope now, but the intercept and slope is going to be on the log odd scale, right? So I will unpack the implications of all this in a minute. Okay, so that's the model, right? And so first of all, let's try to understand what it means to convert a value, a probability, from the probability scale to the log odds scale. Graphical visualization is the key to everything. Whenever you're trying to understand statistical concepts, try to visualize the ideas graphically. So that's what I'm going to do here. I have created a vector here going from close to 0 to close to 1. So this is all the possible values, well, discretized values of probabilities, this x, right? Then what I did is I converted it to a log odd scale, okay? And so then I just created a data frame that has the probabilities theta and what I'm calling eta, which is the log odds transformation of the probabilities, okay? So you can plot all this. I'm going to show you the plots. I just wanted to provide the figure so that you can see how it's produced. It's basically very straightforward. I'm just using the qplot function in ggplot2 to generate on the x-axis I have the thetas, and on the y-axis I have the etas, right? And so what this gives me, right, I'll show you, is this function here. So I put in the thetas here on the x-axis. On the y-axis, I get the log odds equivalent. And you can see that now I've got a continuous distribution here, right, that I can now use in my generalized linear model. So this is a very convenient approach that I can take to model this. And what's even more interesting is, so this is called the logit link function, right? It's a function that takes as input the probability and returns the log odds, okay? That's called the logit link, right? The inverse of the logit link is called the logistic function, and it takes as input the eta values, that means these log odds, and gives you back the probabilities, right? So that's actually pretty easy to do if you can imagine how this would work, right? So let me show you. How can I figure out what the probabilities would be in this kind of model that I've written out here? Let me write the model out again just to be clear. Right, so the model I actually talked about was that I've got log of theta 1 minus theta, right, is equal to, on the right hand side I have some terms alpha plus beta blah blah blah, which I will just write as mu, right? I could just expand that to alpha plus beta whatever centered set size, right? So this is just an abbreviation just to make my life easier as I write out this story, okay? So now how would I figure out the problem to be solved is solve for theta. How do I do that? Algebra to the rescue, right? Exponentiate both sides. Get rid of the log. If I exponentiate the log, right, I get theta over 1 minus theta, right? There's a bracket missing here. And then I exponentiate the right hand side as well, right? So then I get exponent of mu. Okay, so this guy disappears. So on the left hand side, I've got theta over 1 minus theta. And on the right hand side, I've got exponent of mu, right? What do I do now? I'm trying to solve for theta, okay? So let me multiply both sides with 1 minus theta to get rid of that annoying denominator. And so I end up with theta on this side, and I end up with 1 minus theta times exponent of mu on the right hand side. So how do I proceed now? I'm still trying to solve for theta, okay? So let me open up the brackets on the right hand side. So I get exponent of mu, right? This is just simple math now. It's not very exciting, right? But the result might surprise you, right? So I think I did this correctly, yes. And so on the left hand side, I've got theta. And on the right hand side, I've got exponent of mu minus theta exponent of mu, right? I want to get all the theta terms on one side, right? So how do I do that? I add theta exponent of mu to both sides. So I get theta plus theta exponent of mu. You can see where this is going now, right? Because if I end up here, now what do? I still want to solve for theta. So what do? I take out the common term theta out of this picture, right? Got theta 1 plus exponent of mu, right? And there's a bracket missing again. And then I've got exponent of mu here, right? And lo and behold, I can solve for theta by just saying exponent of theta, right? Exponent of mu. I'm sorry about that. Confused this. Exponent of mu, right? And divided by 1 plus exponent of mu, right? So what this means, the practical implications of this are huge, right? Because once I have estimated my parameters on the right hand side of the linear model, right? These A and B parameters, once I've estimated these guys, right? I have mu. For every possible set size, I can compute mu. And therefore, I can go back to the probability space and investigate the implications of my model predictions in the probability space by using this equation, right? So this is just the inverse, of the link function, and that's this guy here, right? You plug in the theta, the etas, and you get back the thetas, right? That's the basic story here, right? And this code is only there for your convenience to reproduce the plots if you want to understand how to produce these plots, okay? All right, so now that I've explained the basic idea behind this logistic regression model, I'm going to now decide on priors and then start fitting the model.